Welcome to a new session on the massive open online course Introductory Concepts of Digital Computing offered by Swayam. In the last session, we have discussed about adder circuits, in particular half adder, full adder and parallel binary adder. Now, we are going to study about two more different adder architectures, ripple carry adder and look ahead carry adder. We know that a half adder can be used to add 2 bits, and using a full adder we can add 3 bits. But in real life we need to add numbers having more than 1 bit. During the discussion on adder circuits in the previous class, we had already seen that to add 2 n-bit binary numbers, parallel binary adders can be used. These parallel adders can be classified into two, ripple carry adder and look ahead carry adder. This classification is based on the way they handle the internal carries from stage to stage. At a glance, both adders looks similar and also has the same set of inputs and outputs, but it differs in terms of performance. The look ahead carry adder is more faster compared to the ripple carry adder. Ripple carry adder. A ripple carry adder is one in which the carry output of each full adder is connected to the carry input of the next higher order full adder. Here, the carry out, say Ci, produced by a full adder serves the carry in for the adjacent full adder. This is the circuit diagram of a 4-bit binary ripple carry adder. Addition is happening from right to left. Initially, Cin is set to as there is no carry in. Now, let us consider two 4-bit numbers, num1 represented as A3, A2, A1, A0 and num2 represented as B3, B2, B1, B0. See the logic circuit where each full adder is named as A, B, C and D. First of all, the rightmost full adder named as A takes the inputs, the least significant bits A0, B0 and the initial carry Cin, and it produces the sum S0 and carry C0. This carry C0 serves as the input to the adjacent adder B along with input bits A1 and B1. The adder B produces the sum S1 and carry C1. This carry is sent to the next full adder for the succeeding stage of addition. That is, the carry produced in each stage is rippled to the next higher order full adder to continue with the addition process, and finally we get the sum bits S0, S1, S2 and S3 along with carries in each stage. In this logical circuit, the carry was being rippled from stage to stage, and so it is called as ripple carry adder. When you observe this addition process closely, you will come to know that each full adder produces its output, both sum and carry, only after receiving the input carry from the previous stage. That means, FA2 can produce its output only after it receives the carry from FA1. Similarly, FA3 needs to wait for output from FA2 and so on. This causes a time delay in the process of addition, which is known as carry propagation delay. The carry propagation delay is the time required to produce the carry output after receiving the carry input, provided the AI and BI inputs are already present. Consider the logic circuit given here. It is a 4-bit ripple carry adder. Assume that each full adder takes 4 nanoseconds to produce its output after receiving all the inputs. So, FA1 takes 4 nanoseconds to complete its processing and produces the outputs S1 and C1. Though FA2 has values on its terminals, it can produce the right output only after receiving carry from FA1. So, it has to wait for 4 nanoseconds and again takes 4 nanoseconds to produce the results. At present, the total propagation delay is 8 nanoseconds. FA3 produces the result after 12 nanoseconds and the final result from FA4 is generated after 16 nanoseconds. So, the cumulative delay is 16 nanoseconds. It shows the worst case carry propagation delay. If no carry occur between stages, then propagation time is reduced because it just needs time to transform input data bits to some outputs. The carry may not occur between all stages, but the worst case must be anticipated. Now, we are moving on to the next topic, look ahead carry adder. It is also referred as carry look ahead adder, and let us see how the carry is handled there to speed up the addition process. Look ahead carry adder. The drawback of a ripple carry adder is the carry propagation delay. Due to this, the processing speed gets limited. Addition process becomes slow. How can we overcome this? The root cause for this is the ripple carry. So, eliminate it, but we just cannot remove it or eliminate it. Rather, we have to handle the carry in such a way that the addition is performed in parallel at all bit positions without waiting for a carry from previous operation. But how? Yes, here comes the concept of look ahead carry. The carry for each full adder is anticipated. So, based on the inputs AI and BI and the anticipated carry CI, the addition is performed. The output carry CI is produced either by a process called as carry generation or by the process carry propagation. What is meant by carry generation? Carry generation means the output carry is generated internally by each full adder. If you recall the addition rules, you may remember that a carry is set only when both the inputs are ones. So, output carry is generated internally by each full adder when both the inputs are ones. This can be verified by using an AND operation, because the AND gate produces a 1 output when both the inputs are ones. So, carry generate can be represented as G equal to A and B or G equal to A dot B. The other process is carry propagation. What does it mean? Carry propagation means the output carry is produced from the carry rippled from previous stage. It produces a 1 when either AI or BI is 1 or when both inputs are 1. This is nothing but the logical OR operation, and this can be written as carry propagation P is equal to A or B, or you can write it as P equal to A plus B. By the help of these additional combinational circuits such as AND and OR, the intermediate carries are calculated. See now, the intermediate carries are calculated directly from the inputs rather than from the previous carries. Finally, the addition is performed. So, the carry output of a full adder can be expressed in terms of Gi and Pi, where Gi is the generated carry and Pi is the propagated carry. If this is the case, when do you get C out as 1? There are two possibilities. Either the generated carry Gi is a 1 or the propagated carry Pi is a 1 and the input carry Ci is a 1. Let me repeat, either the generated carry Gi is a 1 or the propagated carry Pi is a 1 and the input carry Ci is a 1. You may convert it to a Boolean expression such as Ci plus 1 is equal to Gi plus Pi dot Ci. Based on this, we can write expressions for C out of each full adder. C1 is equal to C naught P naught plus G naught, let it be equation 1. C2 equal to C1 P1 plus G1, let it be equation 2. Then C3 equal to C2 P2 plus G2, let it be equation 3, and C4 is equal to C3 P3 plus G3, let it be equation 4. Here, as you know, C0 is the initial input carry and C1, C2, C3 are intermediate carry bits and C4 is the final carry out. Let us try to build the expression for each carry bit so that each carry will be calculated independently. We know that C out of the first full adder, that is C1, can be obtained by the expression C1 equal to C0 P0 plus G0. Let this be equation 1a. What about the second full adder? We know that C2 equal to C1 P1 plus G1. This is equation 2. Substitute for C1. Then we write C2 equal to C0 P0 plus G0 dot P1 plus G1. Hence, we get C2 equal to C0 P0 P1 plus G0 P1 plus G1. Let us call this equation 1b. Then for the third full adder, the equation for C out is C3 equal to C2 P2 plus G2. Substitute for C2 and we obtain C3 equal to C0 P0 P1 plus G0 P1 plus G1 dot P2 plus G2, and hence the expression becomes C3 equal to C0 P0 P1 P2 plus G0 P1 P2 plus G1 P2 plus G2. Similarly, we obtain the final carry out and the expression is C4 equal to C0 P0 P1 P2 P3 plus G0 P1 P2 P3 plus G1 P2 P3 plus G2 P3 plus G3. When we observe these expressions carefully, we can see that the C out or carry output from each full adder is dependent only on the initial input carry C0 and Gi and Pi functions of the same stage. Already we have seen that Gi and Pi values can be expressed in terms of corresponding A and B inputs. So, in this case you do not need to wait for the output carries to be generated for the next stage addition, or we can say that addition at different stages can be done in parallel. Thus, a look ahead carry adder helps to achieve the result without waiting for a carry to ripple through stages and hence speeds up the addition process. Let us see the implementation of this 4-bit look ahead carry adder. C out of each full adder, that is C1, C2, C3 and C4 can be implemented using logic gates and can be connected to corresponding full adders. Let us first design the carry outputs. See, C1 equal to C0 P0 plus G0. You know that this can be designed using an AND gate with inputs C0 and P0 and one OR gate with inputs C0 P0 G0, and hence we obtain the circuit for C1. Next, the carry generator circuit for C2 can be implemented using two AND gates and one OR gate. Inputs for the first AND gate are C0, P0 and P1. To the second AND gate, the inputs are G0 and P1. Then the results are ORed. So, this is how we implement C2. Similarly, we implement C3 and C4 too. C3 uses 3 AND gates and 1 OR gate. Inputs for each AND gate are C0, P0, P1, P2, then G0, P1, P2, then G1, P2 and G2 respectively. In the same way, C4 uses 4 AND gates and 1 OR gate to implement the circuit. Yes, now the carry circuits are ready. But let me ask you, from where do you get these input values Gi's and Pi's? In the earlier part of this topic, we discussed the same, right? Gi's are carries generated and can be represented as G equal to A and B or G equal to A dot B. So, Gi equal to Ai dot Bi. What about Pi's? They are carries propagated and can be obtained by P equal to A or B or P equal to A plus B. So, Pi equal to Ai plus Bi. Let the two forbit numbers are A1, A2, A3, A4 and B1, B2, B3, B4. Now, Pi's and Gi's can be obtained by a single AND gate and single OR gate at each level. These circuits are connected to the full adders to implement a 4-bit look-ahead carry adder. Now, look at the logic design given here. We have two 4-bit numbers A1, A2, A3, A4 and B1, B2, B3, B4. For each set of positional bits, we use a full adder. So, A1 and B1, the LSBs are connected to the first full adder. The sum sigma 1 is generated. Then observe the diagram carefully. The A1 and B1 inputs are ANDed to obtain G1 and ORed to obtain P1, and the same is done at each level. And these results are used as inputs to implement the carry logic. And you know that the carry generated at each level is to be used for generating the carry in the next level. But all these are produced from Ai, Bi values, and hence no need of waiting for a carry to ripple through. The symbolic diagram of a 4-bit look-ahead carry adder can be drawn like this, with 4 full adders and 3 combinational circuits to generate carries. I hope that it is clear now. The major advantage is no propagation delay in look-ahead carry adder, but the disadvantages are it involves complex hardware and it gets more complicated as the number of bits increases. Now, consider the case where we need to add numbers having more than 4 bits. If we follow the same approach, as you know, the implementation becomes too complex. But for sure the situations will arise. How can we solve this? The solution is to cascade these adders or use these adders in chain. So, the 4-bit look-ahead carry adders can be cascaded to add binary numbers having more than 4 bits. This expands their capability to handle the binary numbers. Here, the output carry of one adder is connected to the input carry of the next. Hence, a condition of ripple carry occurs between the 4-bit adders. At the same time, each 4-bit individual adder is free from this rippling and hence from the propagation delay generated inside. So, when 2 or more such adders are cascaded, the resulting logic circuit is going to be a combination of look-ahead and ripple carry adder. The process of carry look-ahead is internal to each individual adder, and ripple carry feature comes into picture when there is a carry out from one of the adders to the next one. So, we come to the end of the topic adders. Let me summarize. During this session, we have gone through the electronic circuits that help to implement the addition of 2 n-bit binary numbers. We discussed ripple carry adder and look-ahead carry adder. The look-ahead carry adder is also called as carry look-ahead adder, and in short we write CLA. Both of these adders belongs to the category of parallel binary adders. They have their own advantages and disadvantages. The major drawback of ripple carry adder is its propagation delay. That is, in each stage the full adder waits for previous stage carry out to proceed further. To overcome this shortcoming, another adder circuit is introduced, that is look-ahead carry adder. In this adder, we have an additional combinational circuit which will calculate all the intermediate carries at once as soon as it gets the bits for addition. The basic idea in carry look ahead addition is to calculate the required intermediate carries directly from the inputs and initial carry rather than from the previous carries. We have come through the design of logic diagram and other important aspects of carry look ahead adder. The major drawback of this adder is the complexity in the hardware. Also, we have seen the cascading of these adders to perform addition of binary numbers having more than 4 bits. Then it becomes a combination of look ahead and ripple carry adders. Here I conclude the discussion on adders. I will join you with another important combinational circuit, subtractors, in the next class. Thank you for watching. See you in the next session. Bye.